Assalamualaikum. Good morning, everyone. Welcome to my lecture number 13 for CHM 577. And for this lecture 13, I'm going to talk about crystal defects or defects in structures. Thank you to Dr. Amalina for preparing the notes, which I have enhanced and now presenting to my students. As an introduction, I would just like to explain that any materials or any substance that we see looking like well-ordered crystals, usually they contain some kind of imperfection, arrangements of atoms, ions, or molecules in those materials or substances is not perfect either at macro level, the big one, or at micro level, the small one. Substances may contain a number of different types of crystalline defects at the atomic level. And perfect crystals very rarely exist, and even the best crystals have at least 1 parts per billion of defects. Now, what are defects? Defects are actually quite important in many processes. For example, in the process of diffusion, deformation, and many others later. Towards the end of the lecture, you're going to learn that. So what are defects? Defects are imperfections or mistakes in the regular repeating pattern that can be classified in terms of their dimensionality, either being point defects or line defects or extended defects. Defects, even in very, very small concentrations, can have a dramatic impact on the properties of a particular material. So why do defects form? What makes these things occur? Defects occur spontaneously simply because by creating defects, the entropy or the measure of randomness or delta S of a particular substance is increased. And using this equation, delta G, which is the Gibbs free energy, delta G equals delta H minus T delta S, you will see that if the measure of entropy or the randomness of a particular substance is increased, then the Gibbs free energy is decreased because you are extracting or subtracting a bigger number. As you can see, when we plot energy against equilibrium or the number of defects, plotting energy against number of defects, you will see that as defects increases, the enthalpy increases. As defects increases, the free energy will go down to a certain minimum and then it goes up again. Similarly with the entropy. So it is very clear through the plot that we see in this yellow diagram that a minimum value of delta G of Gibbs free energy is reached at an optimum concentration of defects. And in this case here, in the case that we see in this yellow, you will see that the minimum value of G of Gibbs free energy is achieved at a certain equilibrium number of defects, and that is the best amount of defect for a particular substance. Therefore, a structure with defects is more stable. Maybe you have met this before, which we know that reactions are favorable when they result in a decrease in enthalpy, and most importantly, an increase in the entropy of the system. So when you are increasing entropy of a particular system, then you are making that reaction very favorable. So when both of the conditions are met, then the reaction is said to be occurring spontaneously. So a negative or an increase in entropy is very much favored. Oh, this is going too far. Now, what are the types of defects in solid? Now, there are two types, or generally there are two types of defects in solids. One is called extended defects or line defect, and another one is called point defects. Now, extended defects or line defects are the defects or imperfections that occur throughout the whole crystal. So you know that a crystal structure is something that is three-dimensional, it is repeated, it's got a pattern. So when you have a defect that occurs throughout the whole of that crystal, so that defect is classified as an extended or a line defect. So extended defects cluster together to form lines or planes. Yeah. And the second type of defects is called the point defects. Now, the point defects are defects or imperfections that are confined to single crystallographic site. So it does not occur throughout the crystal, the whole crystal. It only occurs in certain point of that crystal. And for this kind of point defect, you have two classifications again. One is called intrinsic defects, and another one is called extrinsic defects. Now, intrinsic defects occur in pure substances. Only pure substances have intrinsic defects. And intrinsic defects do not involve any change in the overall composition of that substance, whereas extrinsic defects are due to impurities. When impurities are introduced or when there are some kind of vacancies, then it is called an extrinsic defect, and usually it will involve changes in the overall composition of the substance. So let me first introduce to you line defects. Now, line defects are called dislocation. Dislocation maksudnya teralih ataupun terberalih in Malay. Now, line defects occur mostly due to misalignment of ions or presence of vacancies along a line. So all that impurity or imperfections occur along one line. So when lines of ions are missing in an otherwise perfect array of ions, an edge dislocation will appear. So this is a schematic occurrence of line defect in zinc, which is hexagonal close packing, HCP. Before deformation happens, your zinc will look perfect, nice and rectangular, no deformation. But when you elongate or when you pull that zinc, when there is a tensile elongation, you are going to notice that your metal or your zinc starts to have line defects, which are slip steps physically evidenced at and it's occurring at a large number of dislocation, and this dislocation occurs slipping along the closed pack plane. So this is the picture of a line defect after a tensile elongation of a perfectly aligned zinc. So that's one example. That's one example, and there may be many other examples of line defects. Yeah. So next, I'm going to go into point defects. Do you remember what are point defects? So let's revisit. So point defects are defects that are confined to single crystallographic sites. So it only occurs at one place. It does not get extended to other places. So point defects, as I was telling you, uh, um, has two different types. One is extrinsic, where you have of substance, impurity in your substance or vacancy in your substance. And the second one is intrinsic, which occurs imperfection within a pure compound. Now, going back to your extrinsic, the occurrence is either through a vacancy in the arrangement of molecules or atoms in that substance. There is a vacancy or there is an impurity. So when there are vacancies or impurities in a particular substance, that kind of defect is called the extrinsic defect. For impurity, again, it is divided into two, either interstitial or substitutional. I'm going to go through that later in the next slide. And for intrinsic defect, i.e. defects that occur within pure substance, there are two common types that you can encounter. One is called Frankel defect. The other one is called Shortkey defect. These are names of people, names of scientists who discover these defects. So Frankel defect and Shortkey defects are two types of intrinsic defects within pure substances. So point defects really are about atoms or particles that are missing in irregular places in the lattice in terms of vacancies, impurities, or interstitial, confined to particular sites and does not occur throughout a crystal systematically. So point defects are when you have atoms missing or located in irregular places in the lattice, either in terms of vacancies. Interstitial. What is interstitial? Now, interstitial is in between. So when you have, for example, two atoms making uh, crystal arrangement, they are arranged nicely. So the space between those atoms, they're called interstitial, in between places, yeah? And also impurities. Now, the simplest form of point defect is vacancy or vacant lattice site. So you have something missing there. That particular atom that should be sitting in that particular place is missing. So we call that a point defects, a type of point defects. And all crystalline solids contain vacancies. There are so many imperfection in terms of vacancies. Now, the principles of thermodynamics are used to explain the necessity of the existence of vacancies in crystalline solid, the one that I was explaining to you about, the Gibbs free energy, enthalpy, and the entropy. So when the entropy is increased, that process is favorable and spontaneous. So the formation of defects increases entropy or measure of randomness. So the presence of vacancies increase the entropy or randomness of the crystal. Therefore, defects occur spontaneously. Now, we also have defects that are that occurs because of the vacancies, vacant atomic sites in a structure, vacant maybe atomic sites or ionic sites. It's vacant, so you call that vacancy. And vacancies will give result in distortion of the plane. Imagine if you are arranging a ping pong ball nicely together, and suddenly one of the ping pong balls are missing, you taken away, there will be some kind of distortion of that arrangement of your ping pong ball. So vacancies usually will give rise to distortion, and it is the vacancy actually is obviously, through the word, that it is an absence of atom or ions from the location that it should be in a perfect crystal. So omitting atoms from an atomic site, atoms around the vacancy becomes displaced, and tensile stress field produced in the vicinity. So when you have something missing, the atoms will be moved a little bit, maybe to the left, to the right, and you will get some kind of distortion, and tensile stress will be happening within that area. That was the one in here are the point defects that is produced through vacancy. Now my next slide is about point defects that is produced through impurities. So impurities, if you look at this diagram that I'm showing you in this slide, oh excuse me, yeah, you will see that the orange circles and the little blue circles are arranged very, very nicely within the first 2 or 3 um, layers. And suddenly, after the third layer, you see that one uh, uh, unknown something else have been sitting in a place where it shouldn't be. So this is called impurity. And because the impurity or the foreign matter or the different matter sits between the two atoms, it is called interstitial impurity atom. There is another type, which is called substitutional impurity atoms, where you have the places of atoms are being substituted by something else. One is impurity. There shouldn't be anything in here, but suddenly something comes in. It's called interstitial impurity. Another one is when you should be getting a small blue circle, but you're getting a big blue circle in that place. So that is called substitution. The bigger blue circle or ball is replacing or substituting a small blue circle. So that's called substitutional impurity ions. Or you can also have this orange uh, um, ball, maybe anion. Usually the big ones are anions. This orange anion being replaced with a big blue, light blue anion. So that is also called substitutional. When it is being replaced, it is called substitutional impurity ions. So impurities, impurities are defined as atoms which differ from the host. So when you have a host of atoms that are repeating in its arrangement, suddenly you have something else, so that is called impurity. That something else is different from the host. Now, all real solids are impure. This is something that you have to realize. Very, very pure metals have 99.9999% impurity. So if you look at this, 1 atom per a million atom will be impure, will be the foreign matter. So even if that particular substance is said to have very, very high purity, it still has something else in its structure. That impurity may be intentional, it may also be unintentional. For example, if you put a little bit of carbon atom in a small amount within iron, then that iron will become a steel. Yeah, steel. Steel is stronger than iron, whereas when you have boron in silicon, it will also change the properties of that material. So by putting in different impurity or different atoms into your substance, either intentionally or non-intentionally, you will change the property of that particular material. Putting carbon in iron, making strong steel, and putting boron in silicon will change its electrical property into semiconductor maybe. Yeah. So next, alloys. When you talk about alloys, alloys is when you mix one metal with another metal. Carbon with iron is not an alloy because carbon is a non-metal. An example of an alloy is a deliberate mixture of metals when people with intention mix two different metals together in different ratio. For example, sterling silver is 92.5% silver, 7.5% copper. So when silver is mixed with copper in this ratio, you get sterling silver. And sterling silver is a lot stronger than pure silver. Pure silver is soft. But when you put a little bit of copper in it, you are increasing the strength or the hardness of that silver, making you get a sterling silver. So that's about impurities. So not all impurities are bad. Some impurities are very much desirable. Now I'm going to talk about interstitial. Interstitial, as I was telling you earlier, is space in between. Interstitial defect occurs when an atom or ion is placed in an interstitial site. So have a look at this, for example. Yep. You see here, you have a bunch of brown atoms arranged in a beautiful arrangement, repeated, three-dimensional, and suddenly you get a yellow. Originally it's not yellow, it's red, so I'm changing it to yellow so you can see it properly. Suddenly you have yellow in the place of brown. So this is called, and in that place, so it is called an interstitial defect. This is when you have a foreign atom sitting in a void. Void is an empty space. In a void of a crystal, for example, carbon sitting in the octahedral void in the steel, face-centered cubic, carbon and steel. So it is when you have an extra atom positioned in between atomic sites. So this is picture down here. This picture down here is when you have an atom that should not be sitting where it is sitting at the moment. Can you see? Oh, excuse me. Can you see that this atom is not sitting where it should be? Yep. It is sitting in an interstices or in between space. So this is what's called self-interstitial. And self is when the same atom goes into the interstices where it shouldn't be. Whereas you have foreign atom in here, that is not called self-interstitial. Yeah. And again, if you look at this, when you have an atom sitting where it shouldn't be, you're going to see that the plane or the arrangement or the shape of that particular substance will be distorted. The arrangements of the atoms will be distorted. And so self-interstitial will induce distortion of planes in the atomic arrangement. So I'm going to then go into point defects where you have self-interstitials and impurities. So here is an example of a few different types of defects. Now, number one is called the defect that is occurring through vacancy. So where is it? It is here. Yeah, can you see number one there? Yep. When you have a vacant site and you see that this atom down here is sliding southward and this atom down here sliding northward, and on the right it's coming on to the left, and the one atom on the left is shifting a little bit to the right. So that is actually the changes in the arrangement of atoms that occurs through the existence of a vacancy. There is a vacant position here, so all the atoms around that area is shifting a little bit. Now, number two is called self-interstitial. This is it here. So maybe this atom there goes to this position here, and putting in the same atom in a place where it should not be also will create some defect, point defect. So number two here is when you have self-interstitial, and you can really see that the four atoms surrounding that atom that orang kata menyibuk, it goes in where it shouldn't be. The surrounding atoms also get pushed away and creating some kind of defect. Now, that is number two, which is self-interstitial. Number one was vacancy. Look at number three. Here is number three, is when you have impurity sitting in an interstices. Yeah, you have something else coming in and sitting there like a settingan, like somebody who doesn't belong in this crystal. So that is the defect that is caused through interstitial impurity. Whereas situation number four and situation number five is called substitutional impurity, where this number four is getting a small atom substituting a regular atom, whereas number five is getting a big atom substituting a regular host atom. And the arrows that you see here, these red arrows, is actually telling you the kind of stress, the local stress that is introduced by the defects. So you can see putting in a self-interstitial, you are going to put stress onto that side by forces going outwards. Number four, because the impurity is small, so you get forces coming inwards. Whereas number five, when the impurity is big, the impurity is big, so you have the forces pointing outwards, and so on and so forth. So self-interstitial, which is this one here, it introduces a large distortion in surrounding lattice where the energy of self-interstitial formation is about 3 times larger than that of the vacancy. Therefore, the equilibrium concentration of self-interstitial is very low. It is less than 1 centimeter cube at 300 Kelvin. Yeah. So these are the 4 types of point defects that you might encounter: vacancies, self-interstitial, interstitial impurity, or substitutional impurity. I hope you can distinguish between the four. Now I'm going to next go into defect structure, where you have stoichiometric crystal defect, intrinsic, or non-stoichiometric crystal defect, extrinsic. Now let's go into the intrinsic defects first. When there is enough number of anion. Now we are not talking about metal substances here. We are talking about salt. Yeah, salt, where you have anions and cations. For stoichiometric crystal defect or intrinsic defects, there is enough number of anion per cation to balance the charges. And there are two types of these intrinsic defects. One is called a Frankel defect. Another one is called Shortkey defect. Remember, this is this spelling Schottky. The pronunciation is Shortkey. Yeah, Shortkey. And then the second type of defect is non-stoichiometric defect or extrinsic defect, which can happen through oxidizing. This is defect structure of salts, yeah, of ionic substance, oxidizing the cation or filling up a vacant anion site using electrons. So let's go through the next slides to understand what this is all about. Now, stoichiometric crystal defect or intrinsic defect for pure compounds, and in this case we are talking about an ionic compound. Shortkey defect is a vacant cation site and a vacant anion site. So you have equal number of cations missing the same number as anion. Yeah, in here, for example, you have a regular arrangement of anion cation in apa orang kata berselang-seli, but suddenly you miss one cation and you miss one anion. Yeah, so that is Shortkey defect, where you take the anions and cations and you place them on surface in equal number, and the stoichiometric effect, that equal number of anions and cation vacancy, they will be randomly distributed, but they tend to cluster because the oppositely charged vacancies occur. And this kind of Shortkey defect occurs most importantly with metal halides, and at room temperature, about 1 in 10 to the power of 15 pairs of vacant in sodium chloride. So 10 to the power of 15 is extremely big. So you only get one Shortkey defect in 10 to the power of 15. So in 1 milligram of sample, you have about 10,000 Shortkey defect. So if you can see here in this diagram, let me make it big for you, so easy for you to see. You see here in the lattice of sodium and chloride, sodium and chloride, sodium and chloride, suddenly you have equal number of missing sodium with missing chloride. One sodium missing and one chloride missing. So this is called the Shortkey defect, where Shortkey defect, you have charge neutrality is maintained within the crystal, because when one negative ion left, another positive ion left, so the whole thing does not experience any change in charges. There are no change in composition either, because the anions and cations that went missing are a pair, a perfect pair. Next, we are going to talk about Frankel defect. Now, Frankel defect is also occurring in pure substances. You do not get impurities in Frankel defect, neither you get any impurities in Shortkey defect. Yeah. Now, Frankel defect is when a cation just takes a walk. Yeah, it just went and put itself somewhere else it doesn't belong. So when a cation, being small, gets displaced into an interstitial void. In here, for example, this little blue ball should be sitting in this interstices, but it's gone and put itself somewhere else. So that is called a Frankel defect. It is when an atom or an ion, it moves into an interstitial site, creating a vacancy somewhere else. Now, Frankel defect is when you take the cation out and cram it into an interstitial site, which is a void between normal atomic position. For example, silver surrounded by 4 chloride will stabilize this defect. Tendency for vacancy and interstitial defect to form nearby pair. It is also a stoichiometric defect. That means there are nothing gone missing. They just go walk. They go somewhere else. So Frankel defects are common in the fluoride structures. For example, CaF2, zirconium O2, and silver chloride. So here, as you can see in silver chloride, this silver has gone somewhere else. It's just gone walking. Dia pergi berziarah gamaknya, raya kan? Raya apa? So as a summary, Frankel defect is when you have a cation out of place. A Shortkey defect is when you have a pair set of cations and anions being missing or vacant. Yeah, this is an example of a Shortkey defect where an orange ball is missing along with a blue ball, whereas the Frankel defect is when your little blue ball goes and puts itself somewhere else it does not belong. So those are the two intrinsic defects that you can get within pure substances. And next, I'm going to talk about a non-stoichiometric crystal defect. If you go back to Shortkey and Frankel, these are called stoichiometric defects. The defects occur without any changes in the formula or in the content of that substance, whereas non-stoichiometric crystal defect are occurring for extrinsic when you have impurities coming or when your cations get oxidized. Now, there is a kind of non-stoichiometric crystal defect or extrinsic defect, which is called oxidizing the cation, that may occur when cation having different oxidation state, for example, FeS. Now, if one of your Fe2 have gone missing and suddenly this is originally Fe2 and Fe2, and suddenly one Fe2 is missing ion, creating a charge imbalance in the lattice. What will happen is, because this Fe2 has, has left the lattice to balance out the charges, two of the ions will get oxidized. Yeah, because 2 plus has gone missing, you need to balance the ions, the charges. So this Fe2 plus becomes Fe3 plus, another Fe2 plus becomes Fe3 plus, so the charges gets balanced. So because of the missing Fe2, 2 Fe2 becomes Fe3. So that is called oxidizing the cation. So as a result, there are more S2 minus ion than Fe2 plus ion in the crystal, making it a non-stoichiometric situation. The exact composition can therefore vary with the formula being approximation. So you are going to have this oxidation happening. So that's about oxidizing the cation. Now the next non-stoichiometric defect is filling up a vacant anion site using electrons. For example, if here at the oxidizing cation, it is the cation that goes missing. But when the anion goes missing, when one anion, for example, in sodium chloride, one of the chloride goes missing, creating a charge imbalance in the lattice, what will happen is an electron will come in, will be found anywhere within the system and sitting there to replace the missing negative charge. So electrons go there. So either when the cations go missing, the other metals need to be oxidized, but when anions go missing, some electrons need to be found and placed in the in this vacancy to balance up the charges. So you get trapped electrons to balance the charges in the case of a missing anion within your crystal lattice. So what are the effects of defect structure? Now, defects can bring in extremely exciting properties of substances. You can get solid electrolytes, you can get semiconductors. So I'm going to go through how solid electrolytes. Now, usually electrolytes mean something that can conduct electricity. And usually solids, except metal, solid solid ionic compound will not conduct electricity. But through the defect situation, you can get solid electrolytes happening. The passageway created can be zigzag or straight channels, which are used as routes for ions to move, allowing the solid to behave as an electrolyte. So when you have cations or anions missing from your ionic crystal lattice, you are creating channels, and these channels can be used for electrons to move. So that is how solid electrolytes can be created. Now, solid electrolytes generally display Frankel defect and can be expected for large, highly polarizable anions and highly polarizing cations of low charge. So usually they just move out of the way, just like when you have an ambulance coming, yeah, all the cars are moving out of the way, and but himpit or crash into a different site. So that is usually how it is like in atomic level to make solid electrolyte. When you get the vacant situation creating a channel or as either straight or zigzag channel or tunnel within your structure to allow electrons to pass through and making your solid to behave like an electrolyte. Okay, another happy occurrence due to a defect is the creation of semiconductors. There are two types of semiconductors. One is N-type, another one is P-type. So let me explain to you what is the difference between N-type semiconductors and P-type semiconductors. Yeah. Now, N-type semiconductors. This is actually happening when you have impurity. When you have impurity, so it would have to be extrinsic defect. Impurities that are electron rich, they are called donor impurities, donor of electrons. Now, solids that contain donor impurities, they are called the N-type semiconductors, where N stands for negative, which is the charge for the extra electron. So N-type semiconductor is when you have extra negative charge, yeah? Because the impurity that is introduced is very, very electron rich. An example is when you put phosphorus integrated into the network of silicon. So you have here, suddenly silicon all arranged nicely. Suddenly there is a phosphorus in the middle. As you know, silicon is from group 4, phosphorus is in group 5. So phosphorus is clearly having more electrons in the valence shell compared to silicon. So these people are all 4 electrons, 4 valence, 4 valence. Suddenly P is 5 valence electrons. Now the extra electron on every P atom can be removed by applying a voltage across the solid. The free electrons can then move through the structure and it can function as conduction electrons. Impurities of this type are known as donor impurities because they provide conduction electrons. So phosphorus in this case are the donor impurity and provides electrons that can be used to conduct electricity, making this N-type semiconductor through the donor. The second type is the P-type. Now, impurities that are electron deficient, they are called acceptor impurities. Semiconductors that contain acceptor impurities, they are called P-type semiconductor, where P stands for positive, N stands for negative when there are too many electrons. P now stands for positive when there are less electrons. An example is when you put in boron integrated into the network of silicon. Again, you have a silicon network here. So in the middle, you put a boron. Now, boron, as you know, is a group 3 element. Silicon is a group 4 element. So for each one of the boron, there is a lacking of electrons. Yeah. So what happens is, when boron is integrated into the network of silicon, there exists a single vacancy in a bonding orbital for every boron atom. So there is one missing electron for every bonding, for every boron atom. So it is possible to excite a valence electrons from a nearby silicon into this vacant. So the electron from this silicon, for example, it can be moved into the boron and to complete this site for 4 electrons. Now, a vacancy created at the silicon atom, yeah, when an electron from this silicon jumps onto the vacant site in boron, you are creating a vacancy at the silicon atom, right? At the silicon atom, and it will be filled by an electron from the neighboring silicon, and so on and so forth. So the electrons are hopping from one silicon to another due to the fact that the boron has a less electron. So in this way, when electrons are hopping from one silicon to another, electrons can move through the crystal in one direction, while the vacancies, or which is called the positive hole. So semiconductors, either you have holes or electrons. when the positive hole move in the opposite direction and the solid becomes electrical conductor. So semiconductors, the p-type is when you have far too many electrons. The n-type is when you have too little electrons. Both situations will make your material semi-conducting in certain situation. Oh, is there any more? So that is the last slide of this lecture. Is 50 minutes lecture. So I think this is actually just an explanation to you or of the kind of defects or imperfections that you might find in solids that can give rise to a certain variety of exciting properties for the solid. So that's all for now. I hope you understand this lecture well, and I hope you are going to be able to find some questions that you can practice your understanding and test it. So thank you very much, everyone. I'm going to stop this lecture here. Have a great time and keep safe and keep up the spirit of online learning. Take care. Bye bye. Assalamu alaikum.